right, we are looking at conditions for regression inference and just talking about the regression model, okay? So if we're going to do some sort of inference, which is really just a confidence interval, oh, I'm writing with white, that's not going to show up, a confidence interval or a hypothesis test, all right? That's what we mean by inference. You have some number of observations, okay? Our goal is to predict the behavior of y given the values of x, right? Predicted y. And what we see is that they need to be independent of each other. Each response is independent. And so you're going to see here, this is my suggested linear is the acronym for linear inference conditions, okay? So they need to be independent, all right? And this one, the mean response y. So normally we say y hat, predicted y, equals a plus bx, okay? This is based on the sample statistics. This would be based on the population, okay, parameter, all right? We use alpha and beta and mu instead of y hat and a and b, okay? And so we're saying that it's a straight line relationship, so it needs to be linear. So the first one is the acronym, linear, okay? The standard deviation is the same for all values of x, okay? So notice, this is like my x and my y, and what you see is the standard deviation of this around the points going above and below is the same whether you're in the beginning of the line, the middle of the line, or the end of the line. The spread around your line is the same. So equal spread, okay? So that's that next condition. All right, standard deviation. And then for any fixed value of x, so pick this x, and you look at the y values, and you're like, oh, that's just a normal distribution around that, okay? And so we see normal, okay? And obviously, R is for random, all right? So linear, independent, normal, equal spread, and random. Liner or linear, okay? And you can use this to be and random. So linear, independent, normal, equal spread, and random are your conditions for inference, okay? Love this picture of like the 3D model just sticking right up, those normal distributions around your line, right? And there's really like an infinite number of these, like no matter what x you look at, all right? Second, if you look at a residual plot, this actually reveals everything. The fact that there is you can't really see the independence, but you can see that it's linear because the residuals are scattered, okay? Independent and random, I'm not so sure about, okay? But normal, do you see like there's like a distribution, right? There's stuff in the middle and then it spreads out, right? So it looks kind of normal-ish right there, okay? And there's not a lot of points there, but there's more in the middle and then it spreads out a little bit, right? Even this one, there's one way up there, but there's a pile in the middle, right? At all of these x's, it's relatively normal, okay? Normal-ish at all x's, all right? And then equal spread, right? It's basically one standard deviation above and below, equal spread the whole way, right? Sometimes there's a little bit, but like 68% is within that little range, equal spread the whole way. So out of linear, out of our liner acronym, a residual plot reveals that it's linear because it's scattered, normalish because it's just nicely equally spread out around at all of the x's, okay? And then you just need to really talk about independent dots, right? Like where did I get this dot from and where did I get this dot from? Did this data have any influence on collecting that data? Probably not, okay? Especially if it's random. So that's the process that we need to do ahead of time when we're going to perform any sort of least squares regression inference, all right? We'll get to more on that in the next video. See you soon.